Welcome to another one of our mini lectures. This is the first video on what will be fluid dynamics. To start with, we will focus on statics and deriving the general equation for fluid statics. Now we start with a small element where rho doesn't change, and rho is the density. Now a mass of a small element here would equal the rho, the density multiplied by the volume, which this here would be volume. As you know, with cubics, width times breadth times height and yada yada, which is the volume element. Here are very small increments of volume. Now with weight we have a minus mgk, which means that the body force on the block is here minus rho multiplied by our volume element gk. Now g is our gravitational force and k is our direction. These are surface forces. Now since dimensions are small, we assume a pressure over each surface is constant and equal to its volume at the center of the face. Now we consider forces exerted on a block by the rest of the fluid. Here we have three examples where here F1 and F2 is acting up and down on this diagram, and the other ones are sideways forces, F4 and F3. Now the pressure is our force divided by area, which is standard stuff. Now for the face FEGH, now delta F equals F1, so our pressure equals P1 pressure. Delta A, our area, is delta X multiplied by delta Y. So force on F1 is equal to P1 delta X delta Y, and F2 likewise is P2 delta X delta Y. So forces F1 and F2 are in direction of minus K and K respectively. So net surface force component vector in K direction is the sum F1 plus F2, which is here. And likewise we can take, that should be an F, the sum of our F3 and F4 and F5 and F6 and so on. So the resultant force, since fluid is at rest, is the vector sum of the body force FB and the surface force Fs, which is 0. So Fs plus Fb equals 0. Body force Fb acts in minus K direction. So since Fs plus Fb equals 0, it follows components of Fs in I and J are both 0. So the pressure 3 equals pressure 4, pressure 5 equals pressure 6. Thus the only change in pressure is in the Z direction. So P is a function of Z. Now to determine how pressure changes, consider the values of pressure at the top and bottom faces P1 and P2. The pressure in fluid at the centre of the top face EFGH is P1, hence P1 equals P Z plus 1 half delta Z, and the pressure at the centre of the bottom ABCD is P2, and likewise it's P Z minus 1 half delta Z, and resolving Fs plus Fb in K direction gives this. Now we substitute P1 and P2, so we get this equation here. Now if we divide this by delta X delta Y delta Z, where none of them can equal 0, we get this equation, which starts to become a little bit more familiar as first principles calculus derivatives. Now as we take the limit of delta X delta Y delta Z, take it to 0, we get the derivative here, the dp of dz, and this is for this part of the equation here. Now hence we get this differential equation, dp of dz equals minus rho g, and this is the basic equation of fluid statics, which we've just derived now from a fictitious fluid cubes. And now solutions of this, as always, pressure, you're going to be integrating this. So yeah, integrating this with respect to Z, and that's the derivation of the basic equation of fluid statics. Thanks for watching, and please do subscribe. I'll have a lot more to come. Thanks.